Hello, hello, hello. Uh, I'm audible, guys. Are we live? Are we live? Are we live? I think yes. Yes, yes, yes. So let's start our discussion. Uh, Hello, guys. My name is Hariom Singh, and this is TLE Eliminators. Today we are going to discuss Edu Round 187, right? So let's get started with problem A, right? So monocarp has n identical boxes. The weight of each box is m, and the durability of each box is by stacking them on the top of each other. Each tower will consist of a positive integer number of the boxes stacked on the top of each other, right? To ensure that no box breaks, the following condition must be met. The condition is that for each box, the total weight of all the boxes above it must not exceed the durability of the box, right? And you have to help Monica find the minimum number of towers that he can achieve, given that each of the n boxes must be used, right? And we have test cases, and the values of n, m, and d are pretty small, right? So basically, uh, in this problem, you were given a box. Suppose this is a box, and it has two properties, right? First is its weight, and other one is its durability, right? So what does weight mean? Weight means that what its weight is, and durability is like how much weight it can store. Right? If you put any more weight which is greater than d, it will break. Right? Something like that. Something like this is here. Right? So what you need to do, you have to stack these boxes on the top of each other. So what do they mean by that is, let's say there's a box with uh, durability 5 and its weight is 3. So let me write its weight in the this form and the durability in red. That is the durability is, let's say, 10, right? So what does it mean? It means that this box has a weight 5 and durability 10. So whatever you can put above it, it should have a weight of at least sorry, at most 10, right? So you can also put two boxes of weight 5 weight above it is 10, and which does not exceed exceed 10, so it's fine, right? But what you cannot do is, let's say uh, there's a box, the same box with you know the weight is 5 and durability is 10, of let's say 6 here, and let's say uh, 9 here. I mean, not 9, let's say 5, right? So what happens here is that the total weight above it is 11. So something like this is happening in this scenario. But in our problem, all the boxes have same weight and same durability. So what we can say about this is that let's just take one box, right? This is some box, and it has a durability of d, right? So I want to to minimize the number of towers. First thing that you can notice is that if you want to minimize the number of towers, then you should put as many boxes on the top of one box as many as you can, right? So it is always optimal to put as many boxes on the top of one box as you can, right? So this is how you can minimize the number of towers. weight of 10, right? So let's say here each of them has a weight of 10 and durability of 20. So this is uh, so these are three so this is three boxes here. You can stack them into two more of them, right? So you can just put this set twice, box here and then two boxes here. Then how many are you left with? You're left with two boxes. Why? Because these are three and these are three. So you total have put it, 6 boxes and then you're left with and then another box above it, right? And our condition is satisfied. Look at here, the durability is 20 and the weight of all the boxes above it is also 20. So it's fine. This one is fine. This is identical to this one, so this one is also fine. Then how many piles did we make? We made three piles as well. The logic is going to remain the same, right? Hello, hello. Is the screen visible now? Hello, guys. Am I audible? Is my screen visible? Audible but not screen. Why is that so? Is the screen visible now? It should be visible now, right? Yes, 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 yes. So let's just restart our discussion, right? That would be more optimal. Okay. So this is education around 187. My name is Hariom Singh, and this is TLE Eliminators. Problem A, right? Monocarp has n identical boxes. The weight of each of the boxes is m, and the durability of each box is d, right? To save space, the total weight of all the boxes above it must not exceed the we can achieve it this way, right? So what does the problem say? The problem says that given a box, you have to attribute as its weight and other attribute as its durability, right? Say maximum weight that it right. If you put more weight above on this box, then these are the attributes of the box. Oh my God. Double. Hello, hello. Oh my God. Double. Hello, hello. Yes, yes. Fine, fine. I think my screen is visible now. It's not black and I'm audible, right? Yes, yes, fine, fine. Everything is fine now. So let's just start our discussion the third time. Oh my- Okay. So this is Edu round 187. My name is Hariom Singh and this is TLE Eliminators. Let's get started. Right, right. The weight of each basically you are given a box, matlab, you are given many boxes and each box has two attributes W and D. W means the weight of the box and the D means the durability of the box. Durability means that how many take, right? If you put one more box above it, it will break, right? Monoka wants to build, so you just put one box, then you place one more box above it, then you place one more box above it. So you just making towers of the boxes, right? To ensure that no box breaks, the following condition must be met, right? For each box, the total weight of all the boxes above it, suppose that if the durability of some box is 20, right? The durability of the box is 20, then you can put two boxes above it, let's say 10 and 10. This is acceptable. Why? Because the total weight above it is 20 and the durability is also 20. So it's fine. But what is not fine is each of which the total weight above is 15 plus 15, that is 30, right? And the durability is 20, so it will break, right? So this is fine, but this one is not fine. Are you guys getting this much? In this fashion, and you have to place them such that no box breaks and what you have to do is that you have to put as many boxes in each tower as much as you can, right? It is suppose that if the durability of the box is, let's say, 30, that would still have worked. Why? Because the durability would have been 30. Sorry, the total weight would have been 30 and the durability would have been 30. would have been 50. Keep putting the box on top of each other as long as you can, right? So as long as you can, you just should keep putting it on the top of each other, right? This thing is all right, right? Right, and one test case. Let's just choose this test case, right? The total number of boxes are 8. The durability of the boxes are 20, and the weight is 10, all right? So we see here, we have a box. All the boxes are weight 10. So weight of all these, each of boxes, tell me this much. Hello, hello, right? So each, so in this case, you can put two boxes above it, right? Why? Because each of them has a weight of 10 and the durability is 20. So total weight above it is 20, right? So this is acceptable, right? Now, what you can do is that you have 8 boxes, right? And but you find place one more box durability. So you cannot place one more box above it. So what we get now is that in an optimal set, you can place at most 3 boxes along with each other, right? Right. And then I can place another similar thing. Now I'm left with 2 more boxes and I can freely, place them anywhere, not anywhere, on the top of each other, right? So this is what I need to do, right? And you can notice that on top of each box, these boxes have a weight of total 3. So the answer for this test case should be 3. Why? Because there is pile 1, pile 2, and pile 3, right? That is an exercise for you, right? And so how do we go about solving this problem in code? that I can place durability. Durability, let's call it dura equal to b, right? So if you look at it, suppose that I say that total number of boxes above it are x, right? Let me call it x. Then can you tell me the total weight above this box? Weight of one box, is this clear? Is this hello hello? This is fine, right? Why is there a lag? Uh, so what we can see is that the total weight you can put is equals to the weight of this box multiplied by this number x. And what do I want? I want this to be lesser than or equal to d, right? So m times x should be lesser than or equal to what? So what does this tell me? This tells me that maximum number of blocks that I can place is equal to d. That's good. Thank you. So we can notice that the total number of boxes that I can place on top of this box is equal to d by m, right? And the floor value of that, right? Now I need to know the total number of piles that I can make. D by m plus 1, box in this set, right? So in total, I am asking what is the total number of total number of boxes in this set? Why? Because I have put it x boxes above one box, right? So this can be written as by m, right, guys? This much should be understandable, right? Now, what I can say is that this set, how many times can I replicate this set? This set, let's say that my total answer will be y, the total number of files that I'm going to make, not greater than or equal to n, right? So what I can write y as, I can write y divided by d by m plus 1, right? and this value of right C value of and then this is going to be our answer. Did you guys get this? So this was it for this problem. So this one, right? So what I did was that I took this value as input and then I calculated the total value of that I can have in one set, right? And then so C by B, then you can write this as A plus B minus 1 by B. And this value is going to give you the same result as C of A by B, right? So I just outputted that and my code worked. It is getting accepted. Right. Uh, problem B. Oh, if I use Chrome browser, then it's fine. So let's switch to Brave now. Sorry, Chrome now. So did you guys get the problem A? Yes, cool. So do you guys have any doubt in problem A? It was pretty simple. So let's move to problem B, right? So it says that define f of x as the sum of digits of x, and integer x is called beautiful if f of x equals to f of x, right? You are given an integer x. In one move, you can choose any digit in the number and replace it with any other number, right? And the resulting number cannot have leading zeros. So your task is to calculate the minimum number of moves required to make the given number beautiful, right? So they have defined a number beautiful as when it satisfies this equation, right? F of that value x should be equal to f of x. All right. So if you think, let's just forget about this problem, right? Let's just investigate what this function f tells you, right? So this function f of x, it takes input as some number x. So input is, and it outputs if your number is, let's say 1, 2, 3, 4. So if your number x is equals to 1, 2, 3, 4, Right, guys? Okay, can I not the opacity? I need to decrease the width, right? And the opacity should be this much. Right, this one is fine. So what I said was, what I said that is that this function x, it takes input some value and it returns you the total sum of digits of this number x, right? So suppose if your x is, let's say 1, 2, 3, 4, 1, 2, 3, 4, then f of x will return you what? It will simply return you 1. It will simply return you 1 plus 2 plus 3 plus 4, right? So this value is 10, right? And now what you're doing in this problem is that in this problem, you're feeding this value f of x again to this function f, right? So basically what you did here is that whatever you obtained f of x here, you just feed it again to f of this function, right? So now again you're going to find f of 10, right? And what happens here that if you find f of 10, this value will be what? 1 plus 0. Why? Because the digits of 10 are 1 and 0. So this value is going to be 1, right? And what does the problem ask you? The problems ask you that this value f of x should be exactly equal to f of x. So what they're asking is that when you calculate this value, that is f of let's say 1, 2, 3, 4 should be equal to f of 2, 3, 4, right? Is this clear to you? Did you understand what this function f tells you? Yes, eyes on me is my ID. Yes. So did you understand this? Right, guys? I think the stream is working fine right now, right? So, so let's just for now, let me replace this value f of x with some value, let's say y, right? So what the problem asks you is that you have to find f of y equals to y, right? Where y is what? Y is again f of x. This problem is very mathematical, right? You do not even need to look at the test cases. You can just do the mathematics and you will be fine, right? So f of y equals to y. We have to find some observations regarding this y only, right? So what can y be such that this f of y becomes equal to y, right? So can you tell me just very simple and very obvious value of y such that f of y will be y, where f is what? It tells you the sum of digits of the number, right? Right. Can you tell me one simple value of y such that this becomes 2? So I'll take that out later. So maybe you can just choose y as, let's say, 8 or any single digit number, right? Because if you choose this value as a single digit number, then y will be 8. And what will be value of f of y? This will be sum of digits of this number. But the sum of digits of this number will again be equal to this number only, right? So f of y will also be 8. And this is where the problem decomposes, right? So what you had to do is that you had to observe if the number of digits, sorry, if the number is a single digit number, right? Like it is 1, 2, 3, or 4 till 9, then f of y will become equal to y, right? Right. So we'll get to your approach, Ghulam Mustafa Khan. We'll get to that approach. I actually also stumbled upon that approach, but that is incorrect. I'll tell you why. So let me explain this much first, then I'll tell, and then I'll address your doubt. Right. So what we can do now is that we have observed that if the number of digits in this number is 1, then f of y equals to y, right? Can we think of any other example where f of y will be equal to y? You can just simulate this process for, you know, let's say from numbers from 1 to 1e6, and you will not find any value of y where f of y will become equal to y. Why? Because whenever you find the sum of digits of a number, so if the number of, let's say if you take another example as, let's say your value of y as, let's say, choose it 89, right? Or maybe some double digit number or triple digit number, 189 or 170, whatever, right? And when you find f of y, this number is going to be smaller than y, f of smaller than y, and this can be proved by induction, right? I just ran the loop and I just brute force that to check whether this value f of y ever becomes equal to y, and it did not pass for any of the test cases, right? So I just thought that it is never possible, right? So you can observe it here as well that 8 plus 9 is 17, and this was 170, so that is 8, right? And you can observe that this value is lesser than this value. And you can notice that for all the values greater than 9, that is, I want to claim that for all the values of y which are greater than 9, or we can say that greater than or equal to 10, f of y will never become equal to y, is never ever going to be equal to y. Is this much clear, guys? Right. This is clear, right? All right. This should be clear. Okay. Then let's just, I'll decompose this problem. I'll just give you one more observation, then you will be able to solve it on your own, right? So we just solved a simpler version of this problem, right? Where we replaced y with f of x, right? Now you can just replace it again and then see that what does y represent? Y represents nothing but, how can I write here? Y is nothing but, can I increase the size? Y is equals to f of x, right? And what does y tells you? Y is sum of digits of x. And what did we claim right now? We just claimed that, what is our claim? Our claim that y should be greater than or equal to 1, or, sorry, and less than or equal to, less than or equal to 9, right? We just claim that y should be a single digit number, right? And what does it tell you? That y is the sum of digits of x. So if you combine these two equations, so if you combine these two observations, what you will notice is that y, sorry, sum of digits of x, sum of digits of x, digits of x that we are calling as y should be a number from 1 to 10, sorry, 1 to 9, right? And that is what you had to do. That's it, right? Is it clear? Yes, it's clear, right? Now, for the implementation part, what you missed was that, right? So what you missed was that we had to replace these digits in their place only, right? So what you're just going to you remove the biggest number first, and then you're going to remove the second largest number. That you can in one move. You have to choose any digit in the number and replace it, right? 6 for 5. If you see here, if you see 6 for 5, right? First of all, let's calculate the sum of this sum, or maybe let's call it y for the notation purpose. What does y represent? It represents the sum of digits of this number. So this is what 6 plus 4 plus 5. What is this number? This is 15. All right. And what is our goal? Our goal is to reduce this number 15 to any value from 1 to 9, right? So what we can do here is that, all right. So you had to minimize the number of moves, right? So you have to calculate the minimum number of moves, right? So can you tell me, is it optimal for me to reduce this number 4 or this number 5? Let's call not, let's take this one example, right? So what is more optimal for me? To reduce this number 6, or should I reduce this number 4? Which number should I reduce? Can you tell me which number should I reduce, 6 or 4? Definitely we should reduce 6. Why? Because when you reduce 6, you will get a delta of, let's maybe delta, I should denote delta as, delta denotes the reduction you can get by reducing this number from some number to some smaller number, right? So if I reduce this number 6 to 1, then what will my gain be? My gain will be, sorry, my change will be 6 minus 1, right? Which is equal to what? This is 5, right? 6. We should reduce 6. So our gain, sorry, our delta, when we reduce 6 is 5. And if we reduce our number 4, then how much we can reduce it to? We can reduce it to 0, right? So delta will be what? 4 minus 0. So that is 4. And we can notice that 5 is greater than 4, right? So after performing one move, we want to find the maximum change we can get, right? And that change can be observed through reducing this 6 only, right? Not this 4. So it is optimal for us to remove uh, the largest number first, right? And someone in the chat was saying that they sorted this because if you sort this number, then the order that you which that was given to you will be lost, right? So right, we should reduce it here, right? So what I mean by that is, if you sort this number, then the problem will definitely become something very different from the given one, right? It will become 4, 5, 6, and that is a completely different problem, right? So are you getting why you should not sort it? Because you have to replace these digits in their place, right? And you cannot just touch the order of these numbers, right? Am I from NCUT? Yes, I'm from NCUT, right? So okay, one more doubt that can come to your mind is that why did we reduce this 6 to 1? Why not just reduce it to 0? We cannot reduce it to 0. Why? Because we cannot have leading zeros. Where was it written? Because the number cannot have leading zero. Yeah. So the resulting number should not have leading zeros, right? So what we are supposed to do is that we cannot reduce the 6 to 0. Rather, we should reduce it to some other number, which is just greater than 0, that is 1. So we can reduce it to 1. But for all the numbers which are not the leading numbers, we can reduce them to 0, right? And from then, and from all of these other suffixes number, right? We should choose the one with the largest value. Why? Because because then only we will get our max delta, right? So there are two objectives. The objective one is so our objective is to choose the largest digits from the given number, right? This is our objective, and reduce it to zero, reduce it to as much as we can. And what does this as much as we can means? Uh, Sorry. So what does this means? Uh, why is it not working? Right. So what does this line mean? It means that if the number that you're choosing, if it is the leading number, that is it is within the front of the number, then you can reduce it to one. You cannot reduce it to zero because in that case you will have leading zeros. Otherwise, if it is not a leading number, right? If it is not a leading number, then you can just freely reduce it to zero, and that would give you the max delta. All right. So this one is fine, right? You guys have doubts, but we can save the first number and then sort and then implement if condition for the first digit. What do you mean by you can save the first number and then sort? Okay, so okay. You mean that you can just keep the first number in that place and you just sort the remaining part, right? This is what you mean, right? So basically, you mean that you're just going to store that you had a two in the first place, and then you will just store all the other numbers. You just sort all the other numbers. This is what you mean, right? Okay, cool. Yeah, you can do that. I mean, this thing is fine. You can do that. So the implementation of this problem is very simple. You just had to observe that uh, for each number to have f of x equals to this number x only, you just had to see that if you replace this number f of x as y, then you have the equation as f of y equals to y, right? And then you can just simply observe that this condition becomes true only if y is a single digit number, right? So single digit number means that it is of the form from 1 to 9, right? It cannot be 10 or 15 or something like that, right? So there are only a few possibilities for y. Then you just observe that what y originally was. Y originally was the sum of digits of x. All right. So since y was the sum of digits of x, you just replace it again in this equation. Then you had sum of digits of x equals to y, right? And then you want the sum of digits of these numbers to be equal to less than or equal to 9 and greater than or equal to 1. So you can do that greedily. So for that to do that, what you can do is that you can just reduce this number, reduce each of the digit to its most reducible form, and the most reducible form is 0 if that number is not at the front, and 1 if this number is at the front, right? And that's what I did as well in my code. So you can see, right? So what I did was that I took this number as string, then I calculated the sum of all the numbers, and note that if the sum of all of these numbers is already less than or equal to 9, that is, it is lesser than 10. As you can notice in this case, the total sum is already 1. Then I do not need to perform any kind of operation. Why? Because f of x will definitely be equal to f of x. The number originally is a single digit number. All right. So I just checked that. Or if the number of digits in this number is 1, right? So all the numbers of the form 1, 2, 3, 4 till 10 till 9 are all fine, right? So if the number of digits in the number is 1 or the total sum is lesser than 10, then you can just print a 0, right? This is very simple. And then I created a vector v where in this vector I'll store how much delta I can get for each digit, right? For example, if we see here, then in the example 645, my vector v will store what? My vector v will store how much delta do I have for 6? 6 minus 1, that is 5. How much delta do I have for 4? 4 minus 0 is 4. And for 5, it is 5. All right. Right. So this is our vector v, which contains all the deltas. Then what you can do, you can just freely sort this array in reverse order, and then you can just take like how many digits you can just take, such that the remaining sum of the numbers becomes lesser than or equal to 9. Right. I did that only. So you can see that I just calculated the integer part of this current digit because my original was a string. Then I checked whether if it is the first value. If it is the first value, then I just push back current minus 1 because I cannot reduce it to 0. As you can see here, for 6, I cannot reduce it to 0, right? So I just have to reduce it to 1. So my value will be current minus 1. Otherwise, I'll have to push current, right? And then I reverse sorted it. That is the greedy choice, right? First, you're going to remove 6, then you're going to remove 5, and then you're going to remove 4. I sorted it, and then I'm traversing on this, and my sum originally has the total sum of this, all of these digits, right? And I want this sum to be lesser than 10, right? So by iterating on all of these sums, I'm reducing them by this current number, and at any point, if my sum becomes lesser than or equal to 9, then I just print I plus cout I plus 1, which means that till 0, till this place, I have removed all of the digits, and right, and if you keep removing the digits from this point, you will have the sum definitely lesser than or equal to 9, right? So do you want me to run this on some sample? Let's just take this one only, right? Uh, so in this case, your original sum was 15, right? Then you can just sort it. So your sorted array B will become what? This will be 554. By sorting, I mean to sort it in the reverse order, right? Then what you can see that you reduce 15 minus 5, that becomes 10. So after this step, after reduction here, your new sum is 10. Now note that you do not have to stop at 10. You have to go on further, right? So you go further and then you reduce it by 5, then it becomes 5. 10 minus 5 becomes 5. And now you can notice that your sum has become 5, right? And that's it. Your sum has become in the value from has come into the range 1 to 9, and you can stop here. So how many digits did you remove? You remove 1 and 2. So your answer should be 2, right? It's 2. And my code did that only. Okay, you do not need to care about the statement. It says that false. It is for my own insanity that I'm able to find the answer in this loop only. If you're a beginner, you can just skip this part, right? Okay, let's move to problem C. This one was a very good problem, I think. Okay, let me take the doubts from the chat. Do you guys have any doubt regarding this problem? I solved A to C in 25 minutes and at D at 110, but I'm still a specialist. I want to become a master. How can I? Actually, you did. Actually, I was not in my form today, and you did uh, D faster than me. So you're actually already a master. I think so. You gave very good performance today. That much I can say, right? Just keep practicing, and you'll improve. That are the only. These are the only golden rules, right? Just keep practicing. Okay, you were serious. Okay, let's just take this doubt regarding how to practice at the end of the stream. I'll be able to share some very gold mine resources to you, which I practice from, and then it totally depends upon your hard work only, right? And how much time do you dedicate to CP in general, right? So problem C. Okay, fine. Problem C. Okay. Test generator. You are developing a test generator. It takes two integers s and m as input, and you need to construct an array A of negative, non-negative integers, right? You have to construct an array A where sum of all the numbers the array you took is equal to s, right? And you choose a number m such that if you take the and of each of the arrays number with m, then you get the number itself, right? So if you have studied bitwise techniques, then this must be very clear to you. Otherwise, I'll make it clear right now. So what we mean by this is, right? Okay. So for each I, the condition is that ai and m should be equal to ai, right? Where and denotes the bitwise and operator. In other words, in each number ai, the bits that are set to 1 can only be in the positions where the bits in the number m are also set to 1, right? And you have to determine whether there exists one such array A. If it exists, the minimum possible value of n you have to find, right? So basically, let's just forget about this part of the problem and focus on this part only, right? Where is it? Yeah. So basically, let's just take one number, 1 0 1 1 0 0 1 1, right? And let me call this number as m, right? And this is in binary form, right? This is not decimal form. All right. Now, what the second statement tells you is that whenever you take the AND of this number m with some number ai, you should get ai only, right? So what they mean by that is, suppose if you have a number, let's say this is 1 0 0 1 and 0, right? And I'm calling this number as a, and definitely all the leading values are 0, right? So what they tell us that m and a, let's calculate the value of m and a. That is going to be 1, sorry, 1 and 0 is 0, 1 and 1 is 1, 0 and 0 is 0, 0 and 0 is 0, and 1 and 1 is 1, right? So this value, if you look at this part, these two values are identical, isn't it? These two are identical, right? Is this much clear? Right, guys? Right. So what do we have here now? We can see that if you notice carefully, that all the bits that are present in A, right? All the positions where the value of this A is 1, then, and all those positions also, the corresponding value of M will also be 1. And this has to hold. Can you think of why this has to hold? Why is it making circles? Let me not make a circle, right? So if you notice carefully, that all the positions where contains a 1 in A must also contain a 1 in M. Alright, so this must hold true. And that is pretty much simple to observe. Why? Because when do you get a 1 in bitwise AND? You get a 1 if and only if you have a 1 in all the numbers that you take bitwise AND of, right? So what does it mean? It means that in order to get a value of a value of 1 in M and A, you should have value of 1 in both of these positions, right? And the problem is telling you that M and A is equals to A for all of these values. So this means that whenever you have a 1 in some position at A, then definitely you should have 1 in M also, right? This much is clear, right? So this was the claim for the second part. Now let's move on to the problem. The problem tells you that you have to find such an array A for which the sum of all of its numbers should be equal to S, where S is given in the problem, and for all of these, for all the elements of the array A, if you take the bitwise AND with M, then you'll get A only. So for in this example, let's just take this value where S is 13 and M is 5, right? Can I have this array? Uh, let's just say M is 13. Wait, no, S is 13 and M is 5, right? So in this problem, you have to find such an array A such that the sum of all of its numbers must be equal to 13 and the bitwise AND of all of these values should be 5, right? If you notice 5, then 5 can be written as 101, right? And you want that all the numbers that you choose in this form, they should have 1 in the position where M is 1, right? So you can have, so like this value is M, right? Right. So what does it tell you? It tells you that whenever you have a 1 in the position of M, you can either have a 0 or 1 in A, but when you have a 0 in this position, then you definitely have to have a 0. Right? This much is clear, right? Because if you observe here carefully, then you had a 1 in M, but if you had a 0 in A, you got a resultant as 0, which is identical to A, right? But if you had a 1 here, that what I was means the same. So basically, let's just move here, right? So what does it tell you? It that tells you that you can either have a 0 or 1 here, a 0 or 1 here, and anything there, right? So one construction that they have given this problem is 544, right? In 544, the total sum is what? 5 plus 4, 9, and 9 plus 4, 13, right? So the total sum is 13. And if you notice carefully, 5 and 5, right? Let's just associate this 5 with this 5, this 5, this 5 and this 4, and this 5 and this 4, right? Then you can notice the value 5 and 5 is equals to 5, and 5 and 4 will also be 4, right? So 5 and 4 can be will be 4, right? If you take the and, then you will get 0, 0. All right, because this 1 and this 0 will be 0. So wherever you have 1, right? Wherever you have 1, you can have a possibility of 1 or 0. But in every place where you had a 0, you have to have a 0 in A as well. This much is clear, right? Why? Why this should be true? Because let's just say that you had m as 1, 1, 1 and 0, 0, right? This was your m, and your a was, in this place you had a 1, but in this place you see a 0, and you mistook it as 1. So in a you took it as 1, and then this 0 you also took it as 0, right? So if you calculate m and a, this will be 0, this will be 0, and this will be 1, right? And now did you see that these values do not match? And at which position did they not match? It's this position, right? It's this position only. So this tells you that if you have a 1 and 1 at some place, then you have a possibility of choosing a 1 or 0 for A. But if you have a 0 in some place of M, then you definitely have to choose a 0 in A as well. This is right, right? This much is clear, right? The contest is dated, right? Unless you register and dated. So this is the problem setup. So how do we go about solving this problem, right? So a general rule of thumb for solving these kind of problems is that you should look at, whenever you see something like bitwise AND or bitwise XOR and something related to bits, you should think in the terms of bits only, right? So how I looked at this problem was that I saw, let's just say M is some number 22. Let's no, let's just do a simpler number. Let's just choose that M is 10. Right. Now follow me very clearly. So what is the binary of 10? This is 1010, right? And suppose that the sum that you want to make is 22, right? Let's just choose 22 here, right? And what is the binary of 22? This is 16 plus 4 plus 2, right? So 16 plus 4 plus 2, right? This is 22. Now, notice that all of these numbers m, sorry, all of these numbers a that you have in this array a, they have a 1 at the position. They might have a 1 at all the positions where m is 1. All right. So if you notice carefully that m, let's just say it is 1010, then this can be written in the powers of 2. All right. So this can be written as 2 to the power 3 plus 2 to the power 2. Sorry, 2 to the power 1. Right. This much is clear, right? Now, one thing that you can notice here, that if you form any array A which contains this M as its supermask, so basically supermask is a term where so mask is something like when you put it above some on binary number and you take AND with it, then all the values where it is going to be 1, those positions are going to be derived from these positions only, right? So if you make any array from this super mask, then you can see that you can have 1000, or you can have 0010, and many other possibilities, right? You can also have 1010, right? Now notice carefully that if you add all of these kind of numbers, which are a subset mask of this m, and you add all of these numbers, then you can see that whenever you have a 0 in m, you're going to have a 0 in all of these numbers, right? So your sum will be, so basically I'm performing a sum operation here, right? Now the sum will be this, right? And whenever you have a 1, you're going to get some number of ones, right? So here you have 0 plus 1 plus 1. So let me write, do not make this complex and carry and take carry. Let's just for now take that this is 2 to the power 1 Let's me call it. So let's just denote this by 1. 1 means here 1 means that this value is present, and 0 means that this value is not present, right? This is our friendly, convention for now in this problem. Now observe here that this position is 0. So what you're going to get, 0 plus 0 plus 0, that is 0. So no value, no bit is present here. Here you can see that you have a 1, right? And if you have a 1, you're going to have some number of ones. So right. So you have 1 plus 1 plus 1 plus 0 plus 1. So this value is also 1, right? Now notice carefully that wherever you have ones, you're going to have ones some number of times, right? And what is the weight of this one? How many times did you get this one? You got this one 2 times, right? And for this problem, and for this position, how many times did you get to this? You get this 2 times as well. Now can you notice that whenever you sum all of these numbers, right? Whenever you sum all of these numbers, this sum will have its prefix, you know. This will be 2 into 10 to the power 2. Uh, so this is 2 into 10 to the power 3 plus 2 into 10 to the power 1. So this is your sum, right? And now you can notice that this sum and this m, can you notice some similarity in these two numbers? They look very similar, right? Can you see this? Can you observe this, guys? Are you getting this? Can you see some pattern in this m and s? If you superimpose all of these values above each other, you can notice that the coefficients of all of these numbers are going to be uh, integers, right? And they're going to be same, right? So this 2 to the power 3 will have 2 to the power 3. Then you have 2 to the power 1. Then you'll also have 2 to the power 1, but just with change coefficients. All right. And it is not possible that at some point you have 2 to the power 4 here and you have 2 to the power 5 here, right? Right. Please can you repeat how you wrote the second? Okay, fine. So if you observe here, then the value of m we have chosen is, let me make it clear. Where is the eraser? Uh, so if you see here, right, this value of m we have here is 10, right? This is clear, right? Now I'm saying that for this value of m, that is 10, what kind of numbers we can have in our array, right? So for this array, what we can have, we just saw here that whenever you have a zero in some position, right? Whenever you have a zero in some position, where is it? Right. Whenever you have a zero in some position, then you're going to have a zero in A as well. But if you have a one in position of M, then you're going to have a one or a zero. You have two choices for that. Right. Right, guys. Yes. Now, for this M, what you can see is that it has a zero here. So for all the position, for all the arrays, for all the elements of this array A, we're going to have a zero. So we have a zero. Now notice that in this sum game, what we are doing is that we are just denoting a zero. A zero means that nothing is here. One means that something is there, right? And we are not assigning some weight to it, right? So if you have a zero here, then you relate it to this zero. Then all the numbers in the array A will have zero. Notice that I have chosen these numbers arbitrarily, right? I have not derived these numbers, right? It's just for example. Now notice that you have a one here. So some numbers from this array A will have one in that position, and other numbers will have a zero, right? So in the first number, we have not chosen a zero. We have not chosen a one. In the second number, you have a one, and then you have a one. So right. So in this game, what will happen? You'll have a 1 and 1, so you'll be denoting it by 1. And how many ones do you have? You have two number of ones. So we noted the weight as 2 and the presence of the 1 as 1. All right, right. Now, notice that here you have a 0, and this 0 denotes this position, right? 0 plus 0 plus 0 is going to give you 0. If you move to this position, then this 1 corresponds to this position. Then you have 1 plus 0 plus 1, that is 1. And how many ones do you have? You have two number of ones, right? Now this is our sum. All right, this is our sum. And how can we denote our sum as? This is 0. So it does not have any weight. So just let's just forget it. This one, what is the weight of this one? This one has a weight of 2. So we wrote 2 into 10 to the power 1. This is 0. We can ignore it. And this is what? This is 2. And what is the weight? It is 2 to the power 3. So we wrote that's 2 into 2 to the power 3. Right? And now I'm telling you is that whenever you compare M and S, you're going to notice that they're going to have some base values which are going to look very similar to you. That is 2 to the power 3. Here you have 2 to the power 3. Here you have 2 to the power 1, right? And you are going to have 2 to the power 1 as well here, right? So their structure will look similar, but you'll have different coefficients, right? Did you get this? Sam. All right, guys. So, so how do we go about solving this problem? So after that, you have noticed this much, it becomes very easy, right? First thing that you can notice here is that whenever you are going to sum all of these numbers of the array A, they are going to be some multiple of this number m, right? What I mean by that is that there. So suppose that since all the numbers are going to share some value of some wherever the value of m as 1, wherever in the bitwise, sorry, in the binary form of m, wherever you have a 1, you're going to have either a 1 or a 0 in the array A, right? And when you sum of all of when you sum all of these positions, you are going to get let's just say the LSB of m is, let's just say this is our m, 1 0 1 1 0 0 and 1 0 and 0. So this is our LSB, right? Right. And all the numbers of our array A are going to share this LSB as well, right? So this LSB is going to come some number of, let's just call it X number of times. Whenever you sum it, zero, 1, 0, all zeros, or it could look like this one, all zeros. Oh, sorry. And then this 0, this 0, this one, and this one, right? All of these are valid elements of the array A. And what I want you to notice is that if you look at this LSB position, this is going to occur some number of times, right? And I want you to notice that this LSB, if you're going to sum all of these numbers, then all of the numbers behind it will have a 0. So whenever you're going to sum it, in the sum, all of these numbers are going to be 0 as well, right? In the sum, all of the numbers before that are going to be 0 as well, right, Sam? All right. So all of these are going to be 0 as well in the sum. And then you're going to have some LSB, and whatever you're going to have, we do not really care about it. So this is that first observation, that whenever you're going to sum all of these numbers of the array A, the LSB of this number m that value in the suffix after this value, all the values have to be 0. What I can also tell you about this is that whenever you're going to find 2 raised to the power LSB of m, this value should divide your value s. So this value multiplied by some value k should be equal to s. Or we can say that 2 uh, s modulo 2 to the power LSB should be 0. Alright, this condition should be true. Is this clear, guys? How did I arrive at this condition? I just saw that all the values after the LSB are going to be 0. So when you go to sum it, in the sum as well, you're going to have zeros, right? And then you can denote that this point is LSB. So this point is also LSB. So the LSB of all of these values should match. And notice that if you have, if you would have chosen the position of LSB as all zeros here, then the LSB would have shifted left, right? It would have shifted left, right? And then LSB should have been moved left. So this value should have been more, and that satisfies this condition as well, right? So S modulo 2 raised to the power LSB should be 0, right, guys? Are you guys getting this? All right, right. Now, what happens here? Now you can just observe that whenever I compare my sum and M, I can just simulate this entire thing for all the prefixes, right? So what I can write here is that suppose my M was this value. This was 1 0 1 1 0 0 1 0, right? This is my value M, and whatever our S is, right? It is going to be some value. Let's just say 0 1 1 0 0 1 1 0 1. No, not 1 0 0. We just saw that the LSB of S should lie before, I mean after the LSB of M, right? So this condition is true, right? Okay, so LSB should be same for M and AI, and we can check the derivative through it. M and AI, they should not be same, they can be same, right? What I mean by this is that these, if you see here, right, in this number, the second number of our AI, the LSB lies here, right? What I claim is that all the LSBs of these numbers AI, they should be before the LSB of M, right? Because you have the possibility of choosing this value as 1 or 0 in both cases, right? If you had chosen 0 in all the positions, then you would have zeros in all of these positions, right? And your first one would have occurred somewhere to the left, right? And whenever you sum it, you're going to have zeros in all of these positions, right? So this is what I wanted to say. Now, what we did for LSP, we can just do it for all the other positions of the positions where M has 1, right? And you just combine it and you'll get the answer. So what I mean by that is, suppose you have this as uh, M as this value and S as this value. Now notice that wherever you have a value as 1, what you need to do is that you have some slots, right? And these slots denote the position, denote the elements of the array, right? And each of these slots will have either a 0 or a 1. And what do you want? You want the sum of all of these positions to be equal to whatever the position, whatever the value is present at the corresponding bit position of S, You want the sum of that multiplied by 2 to the power of weight to be equal to this position, right? And notice that this is possible only if you took something from the prefix, right? So what we're going to do in that each prefix, we are going to check whether that if I see this prefix, right? If I'm seeing this prefix, then I want that for each of these slots, right? My element array should have zeros or one at that all those positions. And when I sum it to the power of to the power some let's say weight, then their sum should give you a one or zero based upon the value that is present in the position of S. Right? Is this clear? Right? So what I'm going to do is that I'll take the prefix of prefix of M, and what do I want? I want that this value times how many times I just the number of times I choose so let's just denote this value as x. Where what does x mean? X means that x means the number of slots in the position I am currently at where I have a one, right? What I mean by that is suppose if you choose this position as let me just move ahead, right? Oh, where did it go? Yeah. So if we choose this position, right? So if I choose this position, then what is the value of x? The value of x is 1 and 2, right? The number of slots where I'm choosing this value as 1. So that is what I have written, right? X means the position, the number of slots in the position I'm currently standing at where I have a, where I have a 1, right? And what I'm denoting this value as? This value. Can you tell me this? What will this tell me? This will tell me the total bitwise positions, sorry, the total sum up to this prefix, and this value should be what? This value should be greater than or equal to what? The prefix of S, right? Because if you have this condition, then if you have some extra ones, you can just propagate it to the right, right? If you have some extra ones, you can just propagate it to the left of this array, so to the left of this bitwise thing, and then you just find, right? So this condition must be true for all of these prefixes, right? What I mean by that is, so uh, point by point, you're just going to choose this prefix, and then you're going to choose this prefix, and then you'll see that how many positions are going to have one in that position, right? So suppose if I choose this position, and if I say that the value of x is 2, then prefix of m is what? This is prefix of m is 2, sorry, 0, and this is also 0. So 0 multiplied by 2 should be greater than or equal to 0. That is true, right? And suppose I move here, uh, and suppose if I move here in this prefix only, then what is my prefix? This is 0 1 0 0, and this is 1 0 0 0, right? So what I'm going to write is that the prefix of m is, what is this? This value is 4. So I'll write 4 into some value x. That value should be greater than or equal to what? This value is 8, right? So what do I need? I need two values to satisfy this position, right? And what I'm going to do, I'm going to simulate this for all the prefixes, right? Then I'll have some inequalities, like suppose that here I got a 2. Suppose that in this position, what will I get? I'll get, this is what, 100 100, that is 0 2 4 8 16 32. 32 plus 6, 32 plus 4 36, multiplied by some value x, and that is going to be greater than or equal to this value. What is this value? Well, this value is going to be lesser than 36, so you'll get something lesser than 36. Let me write 8 plus 16, this is 24, right? And you'll get x is greater than or equal to 0, and that is true, right? This is trivially true. Suppose that in this position you'll get some value. Let's just say that it tells you that x is greater than or equal to 10, right? Now what are you going to do? You're going to just combine all of these inequalities, and you're going to say that x is greater than or equal to 0, x is greater than or equal to 10, x is greater than or equal to 2, right? And you're going to say that this condition holds for what? This holds for all the values of maxes of whatever you got. So 2, 0, and 10, right? You're going to take the max of all of these positions. So this tells you that the value of x should be equal to greater than or equal to 10, right? So I'm going to simulate this process for all of these prefixes, and then I'll take the max value of it. Right, guys? Is this okay? Did you understand this much? Right? So I did that in this problem only. So basically what I did was that whatever I just explained, I just did that only, right? I wrote that the first check tells me that so this value m and minus m denotes the 2 raised to the power LSB thing, right? I just checked whether if this value is non-zero, right? As I already told you here, that this value s modulo 2 to the power LSB should be equal to 0, right? So if this value is non-zero, then you're going to return -1. Then your answer will be this value x, right? Iteratively, I'm finding the max value of this x of all of these answers, right? So in this answer, I initialize it with 0. And for each of these bit positions, what I'm trying to do is that I'm finding the prefix of this. So how do you find the prefix of something in bitwise? So basically, if you have 1 0 1 0 0, and you want to find the prefix of this position, then what you can do, you can just take the AND with 1 1 1 and 0 and 0. This will return you 1 and 0. This is going to be 1 0 0, and all of these are going to be 0, right? So this is nothing but 2 raised to the power something minus 1. So I did that. This is 2 raised to the power something minus 1. And then I'm just finding the prefix and prefix of s and prefix of m, right? And if this value is 0, we can just continue. Otherwise, we can just take the max with ss plus m. So this is the C value, right? We saw here that we have some this kind of inequality, right? X is greater than or equal to a by b kind of thing, right? And we already saw in problem A that in order to find the seal of something, we should do a plus b minus 1 by b, right? So I did that. SS plus mm minus 1 by mm, right? So this was it for problem C. Do you guys have any doubt? I don't think so. Let's move to problem D. Okay, this was fairly simpler than problem C, I think. Propositions of problem C and D could have been swapped in this contest. Like, how many guys solved problem C and D? 3002. You're almost same. So, okay, problem D. So in this problem, Alice and Bob are playing some game. So Alice has some array of numbers and Bob has some other array of numbers. So basically what they're trying to do is that Alice will choose some number from this from his array, right? So he'll choose some number from array A and some number from the array B, and then what they have to do that if she chooses some number x from array A and some number y from array B, and if y is divisible by x, then she'll remove y from the array A, right? And what will Bob do? He'll do the reverse of Alice, right? If y is not divisible by x, then he'll remove y, right? And they after they have done, they just remove y, and they note that they do not remove the value of x, right? When you remove y, you just have to remove the single occurrence of y, right? And the player who moves the last, he's just going to lose. And you're going to tell us the maximum, sorry, which player is going to win, right? So let's just take some example here because that would be create more clarity. So in this example, right, this is our array A. Oh, this is our array A, and this is our array B, right? So basically, Alice moves first. So what she can do, she can just choose, this six, and she can see that six is divisible by three, right? So deletes this six from this array, right? Then you have Bob's turn. Then Bob, what will Bob do? Bob will see that he has a seven. So seven is not divisible by any of these numbers, right? It is not divisible by three, two, four, or something like that, because seven is a prime number. So he'll remove seven. Then you have another number two, and then Alice will see that two is divisible by two, four, and many other numbers. So she'll remove it, and then the array will be empty, right? All the numbers have been removed, right? And then in the Bob's turn, Bob has nothing to choose from this array A, so he's not able to perform any kind of move. So he's just losing, right? So the first in the first case, Alice is winning, right? Similarly, in the other test cases, this one is a little bit complex. I did not read the test cases; I just saw the first one, right? So how do you go about solving this problem, right? So whenever you have some kind of game theory problems, your first focus should be to, you know, make some observations from the problem, right? If you have some set of properties of some numbers, then you should be able to segregate those numbers on the basis of that property, right? So basically, a number can be of three types, right? So suppose that number is, let's say this number is n, right? I'm claiming that it can be of three types, right? So every number n which belongs to array B has three types. The first type is that it is removable by all the numbers of the array A, right? What I mean by that is, suppose that the number n is, let's say, 12 only, right? In this case, you can see that this number 12, this number can be removed by 3, 2, 4, right? So it can be removed by all of these numbers. Why? Because 12 is divisible by 12 is divisible by 3, 12 is divisible by 2, and it is divisible by 4 as well. So 12 can be removed by all of these numbers of the array, right? The first type is uh, 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 any number. Sorry, we should write every number from the array A can remove this number, right? So this is our first thing. So this is our first type of number. What could be a second type of number? Exactly opposite of this, right? So the second type of number could be that this number is can never be removed by any number from the array A, right? So what we can write is that no number from this array A nothing can oh my god, why is this so? Nothing can remove this number. Nothing, no number from array A can remove this number, right? So in this example, you can notice that this number 7, it is not divisible by any of these numbers from the array A, right? So we can notice that this number is falling in the type B, the type 2, right? And then you can have the number C, number type 3, which is that some number is going to remove this number and some number is not able to remove this number, right? So this let's just call this number as mixed. So this is mixed type, right? So what does mixed mean? Mixed means that some numbers from the array A are able to remove this number and some numbers are not able to remove this number. So in this array B, you can notice that 6 is of the type mix, right? Because why? 6 can be removed by 2, 6 can be removed by 3, but 6 cannot be removed by 4, right? Because 6 is not divisible by 4, right? So these were the three types of numbers that can be in this array A, and there is no other fourth type, right? So what does this information tell you? This information tells you that okay, now we have made some observation on the array, right? So numbers can be of three types, right? And how does this information can be used in this game? Notice that Alice can remove the numbers only when it is divisible, and Bob can remove the numbers when it is not divisible, right? So let's just say the number is 12, right? And you are given this array. Can Bob ever touch 12? Bob can never touch 12. Why? Because he cannot find any number from the array A which divides 12, right? So 12 will never be removed by Bob. So Bob will never remove this number. So this number is completely claimed by allies. So this number can only be removed by allies. Bob can never do anything about it, right? Similarly, if you look at this type of number, that no number from the array A can remove this number, which means that this number is not divisible by any number from the array A, right? So we see here that 7 is not removable by any of these numbers, right? So we can notice that this number can only be removed by Bob, right? This number can only be removed by Bob, right? And what about the third type? The third type tells you that it is removable by some numbers from the array A and it is not removable by some numbers of the array B. So either Alice or Bob can remove it, right? Now, can you tell me one thing? Now, since we have separated all of these numbers into three types of, stacks, right? Let's just form three types of stacks where we will put all of these numbers in this array A, right? So the stack one is of Alice, stack two is of Bob, and stack B is their combined uh, Alice and Bob stack, right? So if we notice here, let's just choose another example. Uh, in this example, if we notice 10, 10 can be removed by 2 and 5, not by 4 but not by 3. So it is removable by some numbers and it is not removable by some numbers. So stack uh, AB will contain 10, right? What about 7? 7 is not removable by any of these numbers because 7 is a prime number, right? So Bob will have 7, right? And what about 13? 30 is also a prime number and it is not divisible by any of the numbers on the array A. Then Bob will have 13, right? So this is how we can classify our numbers, right? Okay, what was your approach to avoid TLE? I got TLE for 2, 3 submissions. In this problem, are you talking about problem B? Oh, sorry, D. Actually, this is okay, fine. I think you must have used sets in your solution. I think that would have been, you would have iterated on the factors and then you must have used set to find the numbers whether that they are present in the array or not. Right? Am I right? Yes. So basically, the number of factors for a number are around root n. Then you're iterating on the array B, which gives you m, and then you're finding whether this number is present in the set or not. So that gives you order of m into root n into log n, right? And this complexity is never going to pass. It is very, very this. So basically, you can just see that this is basically n into n raised to the power 3 by 2. Sorry, uh, this is order of m into log n cube. This is comparable to order of log n cube. And this, in general cases, it surpasses 10 to the power 8, right? And I haven't seen any solution where you're able to squeeze in this complexity, right? So what you could have done is that the constraints would have had n plus m. So you could have just created a visited array, something like that, and that would have reduced the complexity from log n to m root n, right? But not n root n. But n root n also fails for n plus m equals to 2 root 6. Well, I think it is squeezable. If the testers allow it, then okay, bunny 6 it, yeah, it might fail as well, right? Yeah, it might fail as well on bunny 6. Basically, what I did was that, okay, let me explain my solution first, then we'll get to the implementation. All right, guys. For 1e5 and 2e5, it is fine. No, n log n is not failing. You must have used something heavy. In my code, I have used n log n only. Uh, okay, you might not have removed the duplicates from the array. That might have been one possible pitfall. Okay, let's just discuss the solution first, then we'll get to the approach. Oh, sorry, implementation. So basically, you can just partition all of these numbers from the array A. You can just partition all of these numbers from the array A into 3 types. Then you can notice clearly that, okay, is it ever optimal for Alice if she's moving that all the numbers that she had already claimed, they are not touchable by Bob. So she can freely remove all of these numbers whenever she wants, right? Similar is the case for Bob. He can freely remove all of these numbers which are in his stack freely whenever he wants. So what they need to do is that compete on this set AB, right? So in this set, what will happen is that uh, all of these two two of these people, Alice and Bob, they will iteratively remove all of these numbers from the set, their common set, sorry, the common stack. And then what we'll do when this stack runs empty, that all of these numbers from the stack AB is empty, they'll move to their own stack and they'll iteratively one by one remove all of those numbers from their stack, right? So this is the most optimal strategy for them, right? Because suppose by induction I'll prove that this strategy is optimal. Suppose at some point Alice and Bob stack, the common stack of them, had some element, let's say X, and it had some element Y. And then Bob had something and Alice had something. So he had X and you had Y, right? Now at some point, Alice chose not to remove the element from this stack. Rather, she chose to remove from her stack. Now what happens here is that since one element got deleted, what Bob would have done is that he would have removed one more element here, right? And when all of these elements from this stack were empty, Alice would have one lesser element in her stack because she chose her previous choice of removing one element from her own stack, right? And that would put her to a disadvantage because now she has a lesser number of moves on her end, right? And Bob has more number of moves on his end, so Bob will eventually win. Did you understand this part? C type reading is really it's okay fine. So this is the implementation for this problem. What we're going to do is that we're going to partition all of these numbers into three stacks where LIs will have all of the numbers which are completely divisible by all of the numbers of the array A, right? So when I say that some number is divisible by all the numbers of some set, I am eventually saying that this number is divisible by the LCM of all the numbers. This is pretty common mathematical property. For the stack of type 2, I'm saying that no number from the array A can remove this number, which means that uh, the GCD, basically we can just see that if some number is, so basically if you have some number and no number divides it from this number, then we can say that this number is co-prime to all the numbers, right? And the third thing, that some subset of numbers are going to divide this number while some other subsets are not dividing this number. So whenever we are forming this kind of three stacks, we can just check whether so and finally, but what is our verdict, right? So basically, Alice and Bob will compete on their common stack. They will eventually perform one by one operations. So Alice will have, so basically the size of the stack is 4. Alice will perform two moves here, two moves of Alice and two moves of Bob, right? And what happens now? Now, since Alice has performed one move, Bob has performed one move. So the sequence is going to look like Alice, Bob, Alice, Bob, right? And after performing this step, again Alice has her turn, right? So what that means is if the number of elements in this stack is even, the common stack is even, then you can just discard this set, right? It is of no use. Why? Because after exhausting all the elements of the array of this stack, of this common stack, they're again back to their own stacks, right? And they're going to repeatedly remove the numbers from their own stack. So Alice can win only if the number of elements in her own stack is strictly greater than the number of elements in the Bob stack. Why? Because suppose that her stack has three numbers. So this three knows the number of numbers, right? Not the number three. And this has two numbers. Then Alice will remove one, Bob will remove one, Alice removes one, Bob will remove one, and now Bob is exhausted. So Alice will remove her last number, and then Bob's stack is empty, so he cannot do anything, right? So Alice wins. On the other hand, if Alice would also have a 2 here, then she would have run out of numbers before Bob. So this is the first case, right? The second case could be in the stack you had odd number of numbers. So basically you had uh, 3. So this is a common stack. A, B, this is 2, this is 1. So what they have done, so what they could do that, so Alice will remove this number, Bob will remove this number, and then Alice will remove this number. Now notice that after exhausting all the elements of the common stack, it's Bob's turn to remove the first number, right? So now Alice can get away with equal number of numbers, right? So now since Bob is moving first, so if this is Alice's stack and this is Bob's stack, Then if they have two numbers here, Elias has two and Bob has two, and he has three and five, then what can happen is that Elias will remove her two, Bob will remove his five, Elias will hit her two, and he will have five. Oh, sorry, not this. This is not going to happen. Since Bob is moving first, Bob will remove five, then Elias will remove two. Now Bob will remove his three, Elias will remove his two, and since now Bob is exhausted, he was not able to perform any move. And since he's the first person to not perform any move, Elias is going to win. So Elias is the winner. So this is W for Elias and loss for Bob, right? So this is what I implemented. So you guys are you guys got the idea for solving this problem, but you are not able to implement it. I think so. Mm, 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 mm. I did a C type of thing, creating a visited array and only going through multiples. I did not create a sieve actually. You created a sieve that was not required, I think. Okay, maybe you must have iterated on the multiples of the number, right? That you're going to call as sieve. Mm, 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 mm. You can just do AB by 2 plus AB and 1 for AB plus. So A plus equals to AB by 2 plus AB and 1 and B plus equals to AB by 2. Okay, then you're going to check whether A is greater than or equal to B, right? So basically, my implementation is much, I mean, it's okay, it's not very good. So basically, I just inputted, let me show my implementation here only, otherwise it will lag. Uh, okay, so I took the input and then you can notice that the number of numbers are n plus m only. So I just created a bound where all the numbers are not going to exceed this bound. Then, okay, fine, I'll explain this first. So basically here we need to partition all these numbers into three sets, right? So LHS set will have all the numbers where each number is going to be divisible by all the other numbers, right? So basically, as I already told, this number has to be a multiple of the LCM. So I'm creating LCM and I'm creating a GCD. GCD is not really needed, right? So I just calculated the LCM, right? And if at some point the LCM is greater than bound, so since we know that the LCM is going to be, so for this number to be divisible by all the numbers, it has to be in this bound only, right? If it exceeds that, it is not divisible. So if it is not divisible, I'm just saying that my all is zero. All is denoting whether this number, whether there exists some number in LHS stack, right? So all will be one only when the LCM is divisible. LCM is within the bound, and some number is equal to the LCM or multiple of some LCM, right? And if all is zero, this tells you that there is no element in the LHS stack, right? So this means that there is no number from the stack such that it is removable by LIs, right? No number is present, which is a multiple of the LCM. So if this is so, I can just make the LCM equal to a very large number. So this is acting as a vague value for LCM, right? Now count A, count B, and mix. So count A denotes the number of elements in the LHS stack, number of elements in the Bob stack, and mix is the number of elements in the mix stack. So this is one optimization that we need. That if so, basically what I'm trying to do now is that I'm going to find all the numbers which are of the type mix, right? How do you find whether the elements are in the common stack of A and B? You're going to just iterate over all the multiples of this array A. So basically, you're going to iterate over 2, your 3, your 4, then the next multiple could be 6, it could be 8, because 6 is related to 2 and 3, and 8 is related to 4. Then you can have 10, basically all the even numbers and 12 and 15 and something like that. 12, 14, 15. 15 is coming from because of 3. So this is going to be your set, right? And what I'm going to do is that all of these numbers are reachable from this array A, right? And then I'm going to do what? I'm going to check whether the elements from the array B are present in this array A or not, from this set or not. If they are present, then some element is going to divide this element. Otherwise, some elements are not dividing this. So the first check that I'm going to make is that, uh, okay, so let's just forget about this. I'll tell you how I computed this. Let's just use this as a blue box, sorry, black box, right? So I'm iterating over the second array B. Then I'm checking if this element is divisible by the LCM. Then this put this element in the aliases stack. Otherwise, some element is going to, I'm going to check whether some element is going to divide it. So that can be checked using the set X. I'm checking whether this element X from the array B is present in the set ST or not. Right? I just computed ST here. If this element is present in the set ST, then I'm sure that some element is going to divide this element. So I put this element in the mixed stack. For example, in this case, 6 is divisible by 3 and 2, but is not divisible by 4. So it will be put it into the mixed stack. So mix plus equals to 1. Otherwise, count B, because no element is going to divide this element. So count B. And then I just told that if the total number of elements in the mixed stack is odd, then Alice should have equal to greater than or equal to Bob. Otherwise, she has to have greater than, strictly greater than Bob. So this was basically pretty simple to get to. All you had to optimize was here is that. So basically, I just removed all the duplicates from this array A, because if some, even if you have duplicates, they don't really matter, right? Because you just need to iterate over the multiples, right? This much is clear, right? I have used set to compute only for unique, as if all elements in A will be 1. It will be n into n plus n complex. But you have removed, so you do not have to, wait. So basically, you're saying that for each element in n plus m, you're going to check whether this element is divisible by all the elements of the array. So for that, for each element, you have to iterate over the entire set, the entire array. That will be in square. But to optimize that, you can just find the multiples of this array, right? So what you can do, just remove all of these duplicates, and then what you can do is that you can just check. So you can just mark all the multiples of this current array, as I already explained here. For example, for 2, you can mark that for 2, 2 is present, 4 is present, 8 is present, sorry, 6 is also present. And up to what? You can just mark it to n plus m, right? This is for 2. Then for 3, what you need to do is that for 3, you can just mark 3. 6 is already marked. You can mark it here as well. Maybe mark 9, right? 15 and 12, 13, sorry, 15, right? You can just mark all of these elements as well. N plus m. All right. Then for 4, since you know that this is already marked in 2, so all the multiples of 4 are already marked by 2. So you can just skip it, right? And let's just say if you had 5 as well. So you could have done is that you have should have marked 5, 10, 15, and so on and so forth. All right. Okay, after using fast input and output at CC. So you're saying that you're a competitive programmer and you do not use fast input and output, bro. Okay, here. So I just did that. I iterated over all the multiples of this set and then I marked them as 1, and we have used that here. Right. So let me summarize this. Basically, in this question, you just had to partition this element into three types, whether the element is completed, is divisible by all the elements from the array A, or it is not divisible by any of the element, or it is divisible by some element and it is not divisible by other elements. And once you notice this, you can just say that the type 1 elements are only touched by allies, type 2 elements are only touched by Bob, and type 3 elements can be touched by both allies and Bob. And then we noticed that it is always optimal for them to first remove all the elements from the common stack before moving to their own dedicated stack, right? And that just completely dependent upon the parity of the number of numbers present in this common stack, right? And in order to mark all the elements in this LIC stack, what you can do is just calculate the LCM of this all the numbers from the LIC stack and check whether some number A B is some multiple of the element LCM, right? And to check whether some element is falling in the type 2, you can what you can do is just mark all the multiples of this LA for this array A. We can just find all the multiples of all the numbers of the array A and check whether some element is present in that or not. So if you do that, you can get the mixed type, and then all the elements of the rest will be falling into the type 2. So this is how you had to implement it. You just need to have the knowledge of how do you iterate over the numbers fast, and then you're good to go, right? All right, guys. This concludes our discussion for this contest, right? So someone in the chat was asking me about how to become master from specialist. So basically, you just can follow some resources like the Stack Guide. Are you there? Yes. So have you heard of the Stack Guide? Right. This is pretty much uh, this contains pretty much everything you need to know to get to master, or maybe beyond that. Since you're a specialist, I tell you that you just focus upon binary search and answer and DP. So you can just start doing DP from here, right? Right. You can just follow all the problems from this discussion from this resource. You can read all of these books. No, not all of these books, just the extract part from that from this. Uh, to just follow this entire thing, and then I can recommend one more thing. That is blogwa.fun. This website. Maybe I should link it in the chat. This website is good. The CACS, sorry, yeah, you can just see DP section here. You can solve all of these problems. This is pretty good. And since they have already added CACS solution as well, uh, you should be solving this as well for DP. And then you also have add code contests, add code DP, right? So basically, what you have to do is just focus on binary search and answer. Maybe learn about graphs and trees if you're not familiar with them. Just learn the basic concepts like the skull prints algorithm, what are the properties of trees, and you have completely solved CSS. Then you should have fairly good idea. What's your rating? Exact rating. Maybe you can just link your profile in the comments and I can look. Topics to reach pupil. There are no topics to reach pupil actually. If you're a newbie, you just follow. You can just you should follow maybe I don't know. Just focus on logic building. I think just focus on logic building and solve more problems. maybe there, if you're stuck on UB for a long time, then you should see that where are you making mistakes. You should upsolve the problems which are not able to solve in a contest. Like in today, if you were able to solve the first two problems, then you should see why were you not able to solve the third problem. Do not care about learning new topics for now because that is not going to be fruitful for you. Okay, you have artist 404. Your graph is not stabilized yet, so you're not stuck. You might improve. Let me look. 2, 3, 2, 3, 3. In depth, you are able to solve 5. On good days, you are able to solve 4 or 5 problems in the depth 3 contest. Okay, you solved 6 once. Which contest is this? Whatever. So I think that you're just not fast. Is that why you're not able to gain rating? You solved it in the 8th way. Yet I think you're just slow. Yeah, you're able to solve the problems, but you're not able to solve them fast. But you solved C1 pretty fast for a specialist. I think you should. Uh, you can look at this. You can just solve this sheet called CP31. That would be, and this is my second profile used to give contest. Okay, you do. Why do you have two separate profiles for giving contest and practicing? Actually, you should, uh, focus on solving more problems of DP. So basically, you can just solve uh, DP, focus on binary search, and what else? You should learn basics of graphs and trees. And since your rating is not stabilized yet, you're not stuck at specialist, you'll get to expert. Uh, in, I guess, I think you'll get to expert if you follow this routine religiously. Just dedicate more time to CP and you can just also think about solving the problems while you're not actually solving them. So basically what you can do is that just read some problems in the morning when you wake up, and whenever you are not doing something active, whenever you're not doing something actively like walking or maybe doing some household chores, you can just think about those problems which are above your rating. You can do problems of the rating 1500 to 1600, and that should be pretty good, right? Okay, do you guys have any more doubts? For Sam, you should focus on logic building and solving more problems. All right, good resources for practicing bit manipulation questions. Uh, there is, I don't think I'm aware of any such good resource for practicing bit manipulation questions, but you have code daily. Codedaily.com. I think they have. Uh, okay, fine. Here, do they have bit manipulation? You can just do maths, and then they have very nice curated resource of problems. You can just solve from here, and I think bit manipulation you'll get better with it as solving more problems, right? But if the sheet that I mentioned 2 minutes ago, this is, I think I Progwa.fun. Okay, I'll link it in the comments. Whatever I recommended. This is a coding.com. This is progwa.fun. Why am I not able to send comments? And you have Yusako Guide and at Coder. You have CSES. Basically, these are one of the most famous websites where you can solve problems from, right? CU was taking people for a long time. Uh, I think around that time, I don't know why I was stuck for a long time. Maybe I was not able. Yeah, the main reason was that I studied a lot of topics which were not very really useful for me. For example, when I was 1100, I used to think that my rating is not increasing. I should learn more topics. So I learned DP and all kinds of DP, but that was not fruitful at all. So when my rating increased, that was due to me solving more problems of my own rating and stop obsessing over learning more topics. So that is one golden advice that I give to other students as well. You should practice more upon your fundamentals, right? Get your first principles right, and then everything will follow along. Well, actually, uh, this okay, yeah, AI is troubling everyone, right? But we can do about it. The main thing is that you should not use AI. That your skills will erode by time if you use AI. Brain rot is real. All right, I should end the stream, guys. Let's have chat some. Let's have chat sometime later. All right. Thanks for joining. Bye bye.